Well, lucky for you, let's make this the last full week of the whole semester. How about that?
That's right. I realized that this morning and I was like,
Last full week ever. For many of you,
It's Geneseo.
the last full week ever. For some of you, Geneseo. For some of you, just the semester. So just to put in context where we're at, after today, we have class on Wednesday, class on Friday, class next Tuesday, a special Tuesday edition of the Wednesday class, and then that's it. Yeah. So in terms of things we still have to do, there's a Kappa due next Tuesday, a week from tomorrow. The cluster project is due next Wednesday, a week from Wednesday. And then our final exam is, I think, the following Monday at noon. Monday, May 17th.
Is that right?
Yeah, TBA on lots of stuff related to the final. I'm planning to have it be like sort of an exam one. I don't think it's going to be cumulative. I think it's just going to cover the last stuff we've been doing.
Can you throw a few easy cumulative questions on that? Like what's the luminosity ratio of these things when I give you the magnitude?
You want some bones?
Yes,
Sorry,
low hanging fruit.
do
we'll
we
see.
have another Kappa before the one that's due on Tuesday?
No.
Oh, okay.
No, there's one more Kappa, the cluster project, and the final exam, plus a couple of Astrobytes presentations. For some of you, is the last things that you have to do for this exam, this class.
Just a bit paranoid. That's Tuesday the 11th, not tomorrow.
It is Tuesday of next week.
Okay, thank you.
Short notice.
Almost gave me a heart attack.
Asking the important guy. You have 11 hours.
No, it's last Tuesday. Okay. Sure. You have nothing due this week. That is correct. You can work on you should be working on both the Kappa. Just to reiterate, you should not wait till next week to do both those things because, well, it's a normal Kappa, but it's the cluster assignment's more than a regular Kappa. So don't put off till next week starting that assignment.
Okay.
Okay.
You say looking right at me.
You were the one who was making the I'm about to die noises.
Well, if the example was due tomorrow night, I wouldn't be that concerned about that. Like you were, I'd be like, all right, yeah.
I mean, you can pretend it's due tomorrow, and then it's done, and it's out of the way, and you're good to go.
I do have other things to do.
Yeah.
Okay. What else should we do today? How about an astronomy picture of the day?
I think that's the one that I was talking about.
This is probably the one you were talking about. This is one of the most iconic pictures that's ever been taken. This is taken in Apollo 11 by Michael Collins, looking back.
Excluding Michael Collins.
This is the picture, indeed, that is every human in the world is framed in this picture, except for one. And that one that took the picture. Oh, thank you. There's always something I forget to do. There we go. How's that? Every person framed in this picture except for one. So this is Neil Armstrong and Buzz Aldrin are in that particular tin can. It has recently landed on and taken off from the surface of the moon and is rendezvousing back with the orbiter that Collins stayed in. Collins is getting prepared to capture it. And I guess he had enough time on his hands to just pick up his camera and take one of the most iconic pictures that's ever been taken of all of humanity, save one. So that's exciting. This, of course, was in 1969, before any of us were born. So none of us were actually pictured in the scene, but everybody who was alive at the time was pictured in the scene. So there you go. Tribute to Michael Collins.
I saw him told Neil Armstrong he should scream, "What's that?" and then just cut his mic out. It's the first thing on the moon. Like, this is why they left Michael Collins behind.
The practical joker. You do not want to be the first person to walk on the moon. That's funny. Excellent. Okay. Pup date. Let's see what the puppies are doing now. If they're active, I'll show you. If not, I will show you a video from yesterday. What's going on with the puppies? Oh, look, it's a sleeping puppy file, which is always happening this time of day. Awesome. So let's see if I took some good. Let's see. Okay, so if you want to see some puppy madness, here we go. I wonder if this is on this, it'll make it a lot easier. Do I have? Yes, I believe I do. Nope, that's not it. Nope, that's not it. Okay, I need to share this. Hold on. Should have done this before class. AirDrop. Oop, done. Just AirDrop it. Do it. Oh yeah. Okay, here it is. So this is my backyard, and the puppy's outside for the second time, maybe ever, just frolicking in the backyard with the other dogs and the people. So here we go. And I'm tripping over them as they're running under my feet and are everywhere, and we've lost all control. My in-laws are visiting for this month. That's them. That's their RV. They just want to be where you are, and so you end up tripping over them if you're not paying attention, which is fantastic. My other dog, who has been terrified of all the puppies pretty much the entire month and a half that they've been alive, has actually gotten to start playing with them outside. He just will get the zoomies and start running around the backyard, and they will try to follow along and bound after him and chase him, and it's actually fantastic. So this is our favorite game. Bowl over the puppies. They just come back for more. It's fantastic. So there you go. So I'm thinking sometime next weekend, maybe Saturday, we'll just have them all in the backyard. You can, and you have to send out an email. You can stop by sometime in the afternoon and come see them. And yeah, get to hold the puppy. I know it's adorable. Okay. Okay, enough silliness. Let's talk about some astrophysics. We left off talking about white dwarfs and how weird they are and how they were discovered and how long it took people to realize what was going on and all the weird properties. This is the types of white dwarfs. Again, I'm not doing this so that you memorize the types of white dwarfs, because I don't remember the types of white dwarfs. But I just want you to show you all of the, in the universe, which is a big place, there are a lot of these things, and there are categories we can break them up into, which are weird and not what you would expect. So let's talk about types of white dwarfs. So there's the DA white dwarfs. This is, again, observation, right? Before we know what white dwarfs are, we take images of them, we take spectra of them, we categorize them based on their properties. And then after the fact, we try to figure out why. So DAs are, we talked about this, what the spectrum would be. Only hydrogen ions for these DAs, right? And this is about 66% of all white dwarfs are in the DA category, 2/3. And series B.
I'm taking this morning.
That's my bad.
That's fantastic. And then there's the DBs, which show only helium lines. And that's about 8%. Then there's the DCs, which show no lines at all. And that's about 14%. And then there's the DQs. I don't know, Dairy Queen or something. I don't even know. Show carbon lines. And then there's the DZs that show metal lines. This one makes sense because Z is the middle thing. I guess they had to choose Q for these carbon ones because C was already taken. I don't even. And somebody like Dairy Queen shakes.
I think there's no lines.
Yeah, that's a good question.
Which is
How do you
like-
get only helium lines? How do you get hydrogen lines?
But it's like.
How do you get carbon lines?
It's like a spectrum, there's just no bits anywhere.
Yeah, I think it's a pretty smooth black body spectrum. Yeah. What is that made of and how does that work? I don't really know, to be honest. And I'm not going to spend much time going into this because I don't really know. A is obvious, right?
I guess it could have like almost no atmosphere at all.
Yeah, maybe. But I mean, it's got to come through something, I would think. Anyway, you know, the gravity, let's think about A, right? We don't expect there to be much hydrogen left. We're talking about the exposed core of a star that's gone through all these processes. But one, it's possible for hydrogen to get dumped back on. And also, not all the hydrogen will be gone. Some will remain. And the surface gravity is so strong on the surfaces of these things that you can have diffusion take place. And so the hydrogen will tend to rise to the surface and the heavier elements will tend to sink if no other processes are going on. So it's not hard to see why you would get hydrogen happening on most of it. It's not surprising that that's typical one. This isn't surprising either. These two aren't surprising to me. We expect perhaps depending on how much of the inner part of the core remains, you might have a helium shell on top of your carbon oxygen core, right? Depending on where those shell flashes happen and what actually happened to move that apart. This shouldn't be surprising. If you have ejected, in fact, everything except the core, you expect pretty much carbon to be left. Yeah, what this is, I don't know. Weirdness. Such is the universe. You make enough of these things, some of them get pretty weird.
I have a not important question at all.
Yeah.
The pluralization for white dwarf. Is it like the surname Butz pluralizing to Butz kind of situation, or do you pluralize it like one would with ethical creature?
That's an interesting question. I think it's an S.
Okay, well, we agree with that it pluralizes with an S, but does the F become a B?
Does the S become a V?
Like,
Does the F
like-
become
like
a
the
B?
summit
Is it
dwarf.
S on that, or do you think yeah, like dwarf?
Like a singular dwarf.
I think it's an S. But this is interesting because I think that
to BES, like replacing the F with B.
yes, no, I know what
Okay,
you're
so
saying.
it's-
Yeah, no, I know what you're asking. This is like I think that Tolkien actually invented the VES for dwarf plural. I think prior to Tolkien, nobody would have ever said anything but dwarfs. And so dwarves, I think, is literally just the Tolkien creature in that sense.
So messed up by like 50 years or
And
something.
I think the same thing with elf, is true with elf, although I'm not entirely sure about elves.
Okay.
So yeah, I'm pretty sure that it's white dwarfs.
Thank you.
Yeah, you're welcome. More important than white. Okay, so what are these things? How do they work? Let's try to derive some physics of degenerate matter. Let's try to understand what's going on with white dwarfs and how they're, what I say electron degeneracy pressure a lot in intro astronomy, and I never really explain it other than things can't get too close together. Let's try to understand electron degeneracy pressure in a class. So degenerate matter. Degenerate matter is any time when you're running into the problem of particles wanting to occupy the same quantum state. That's literally what we're talking about, occupying quantum states. And so we know Pauli exclusion principle. Remember, so no two fermions can occupy the same set of, let's write it down, no two fermions can occupy the same quantum state, and we're really about a quantum state, or can have the same four quantum numbers. And remember what fermions are. Fermions are spin half particles. And bosons are integer spin particles. Bosons can occupy the same quantum state. This is where you get Bose-Einstein condensation and things melding into a single unified quantum state. Okay, so let's think about the physics of degenerate matter. You remember way back in Inlet 3, we derived some equations from thermodynamics by imagining the particles in a box. We're going to do very similar things now for quantum, for degenerate matter. So let's imagine a box. So this is an important slide. So if you have a box of particles, of fermions, and you reduce the temperature of that box to 0, or the particles in that box to 0, the electrons or whatever fermions it is you're talking about have to occupy all the lowest level quantum states in the box, right? And so you will end up with a plot that looks like this. So here is the first, what's called the Fermi energy, and that is defined by how big the box is and what the particles are. But it's a property of the box and the particles and not of the states that the particles are in. If you reduce the temperature of that gas to 0, then let's just call them electrons, can only occupy all of the quantum states that are below the Fermi energy, and all of them will be occupied. And you will have an energy distribution of those particles. Even at t equals 0, those particles, most of those particles can't have E equals 0, because that is quantum state is already taken up. And so some of them will be moving a little bit faster, some of them will be even at t equals 0, some of those particles have to be moving just because of the nature of quantum mechanics, which is weird. But this shows you the energy of those particles at t equals 0. There'll be just a step function. All of these states will be occupied, and none of those states will be occupied. As you increase the temperature of the fluid, of the electrons, more and more of these higher energy states will be occupied, and fewer of these low energy states will be occupied, until eventually you get a nice Maxwell-Boltzmann distribution of energies when you don't have to worry about degenerate matter. But this is one extreme, the completely degenerate case. And the non-degenerate case would be a Maxwell-Boltzmann distribution where you have a nice peak at some point and then falling off on either direction on the energy. So let's try to figure out what this Fermi energy is. Let's try to derive what the Fermi energy is, because that's going to sort of play a big role in talking about what the behavior of these states are in a particular context. So, let's define the Fermi energy. And this is usually this epsilon sub f. This is the minimum energy of any, I'm going to say electron, but this could be any fermion. We're specifically talking about electrons in this case of white dwarfs, but for neutron stars, we could replace this with a neutron, and the arguments would be exactly the same. In a completely degenerate case.
Pardon, aren't neutrons bosons?
No.
Okay, never mind.
At t equals 0. at T greater than 0, some higher energy states are also occupied. Okay, so let's try to derive what's from here. Let's imagine a box with length L, length up. That's all the direction. Okay, and let's think about, again, if you've got this, it's sort of like the 1D particle in a box in quantum mechanics. We know that if the box is truncated, we can only fit a certain number of energy levels in there based on the wavelength of the particle that can fit, that can have nodes at the two edges of the box, right? So we can define the wavelength of these particles in X, Y, and Z. This is going to be 2L over NX, right? And the same with lambda Y and lambda Z. Let's talk about so N is the integer quantum number. So let's just think about where this number comes from. Again, the zeroth state is a node on each side with a single half wavelength in between. Right? That's the lowest energy, longest wavelength line thing that can be there. And that's this factor of 2 comes because you get 2 antinodes, 2 nodes for every wavelength. And then it's just geometry, n divided by. Does that make sense? And we can do that in all 3 dimensions. So you remember the de Broglie wavelength? So the Broglie wavelength is wavelength equals h over p, where p is momentum, and h is just Planck's constant. So this is, for massive particles, sort of the wavelength that you can consider that massive particle to have. So plugging it in, lambda x is 2L over nx, which is h over px. And we can solve this for px. This is without thinking about this wavelength. Px equals h times nx divided by 2L. So this relates an object's momentum to its quantum number in a particular direction, to its quantum number in that same direction. And you of course, I won't write it down, but Py and Pz follow exactly the same. Substitute the x otherwise.
Dr. Steinhauer.
Yeah.
Would there be a velocity term in the momentum?
Yeah, I mean, that is, momentum has a velocity.
Okay, it's just weird to see, I guess, without like m times v.
Yeah. P is a more fundamental property of a particle than mv. But we're going to be getting, so let me break down the next thing I'm on. Let's think about kinetic energy. We know that E, kinetic energy, is 1/2 mv squared. This is also equal to p squared over 2m. So we're more interested, we're going to make, we could do this with p or m, it doesn't really matter. We're gonna make those v's and p's go away, and so it doesn't make much difference how we formulate it. But p, I think most quantum mechanics people, most quantum mechanics, is that what they call themselves? Prefer p to v. It's just a more, I think, intuitive and fundamental property of an object than either m or v. Okay, certainly then B. All right. We also know that, let's come over here. P squared, the total momentum, is just the sum in quadrature of the components, px squared plus py squared plus pz squared. So the kinetic energy is I'm going to take, I have p squared, I'm going to square this thing and put that in there. Except I'm going to square the h and the 2l, and I'm going to leave the nx because this is going to be, let me write this down and let's try to figure out where it came from. I've got h squared over 4l squared. I've got a 1 over 2m. And I've got nx squared plus ny squared plus nz squared. So the 2m is from there. This is the first part of the p squared, and this is sort of like the combined p squared terms up here, from which I've pulled these terms out on all of them. This really is px squared plus py squared plus pz squared, and I pulled out the h squared over 4l squared and just left the nx's there. Okay, I'm seeing shakes of things. That's a good thing. So let's call this, because nobody really wants to write this out anymore, h squared n squared over 8ml squared, where n squared is equal to nx squared plus ny squared plus nz squared. We can sort of think of this as a combined set of these three quantum numbers. So these, although it's different, right? No fermions can have the same, all the other ones plus this, but this is a combination of a bunch of different quantum numbers, and so things can have the same thing. Okay. So you can think of this n as like a distance in n space. It's useful to think about this as like a radius vector, right? From the origin, from the ground state, how far are you in n space away from the origin, from the ground state?
Start at 0 or 1?
These n's have to start at 1, right?
Yeah, because I can't have.
Right. This equation doesn't. Okay. Okay, so let's ask another question. What is the total number we have? So we have the energy of, this is just the kinetic energy of any particle in any of those quantum states. Okay. What is the total number of particles in the box? Because where that Fermi energy is going to be dependent on how many total particles are. Okay, so it turns out that each of these quantum states, though, like even nx1 equals 1, and y equals 1, and z equals 1, can have two particles, because spin can differentiate them between them even in, I think that's it though. That you've got, those are the four quantum numbers, nx, my, and z, and spin. I haven't had quantum since I was in college, so I always make this stuff up and hope that I'm right.
Any other quantum numbers would be caused by, like, if it were orbiting, if it were
right in some nucleus or some other interaction. So those are, for a free particle, these are the four principles. Perfect. So you get 2 in each quantum state. And And by quantum state, I mean like for any specific set of x, y, and z's. So I just put one down, nx equals 1, and y equals 2, and z equals, let's make this also 2, just so it's not so weird. Anyway, this is a particular quantum set. We can have 2 particles, 2 electrons in that particular quantum state, 1 spin up and 1 spin down. So let's think of this as a volume. Let's think of n space as a volume. Ne equals, let me write this down and then we'll try to figure out what all these terms are. I've got a 2 factor of 2, I've got a 1/8, and I've got a 4/3 pi n cubed. So the total number of particles that I can get below a particular quantum level n are, this is the volume of, total volume of n space. Space is about the origin in a perfect sphere. This is the fact that you can have 2 per every quantum number in there. And this 1/8, where does this 1/8 come from? This is kind of fun. None of these quantum numbers can be negative. So we're only talking about 1 quadrant of this spherical volume, and that is the one with the positive quantum numbers. This is not a physical volume, this is a volume of quantum numbers volume. And so we're limited to the positive numbers, which eliminates half of the x and half of the y and half of the z, and leaves us 1/8 of that total volume.
I feel like this doesn't pan out for small capital N. Is this something that it approaches as you get to larger numbers of large
Yes,
N's? So then
it does. That's true.
1, 2, 3, like that you're only going to have like 10 states.
That's true. That's true. It approaches this as n becomes bigger than, significantly bigger than 1, which is going to be the true case for any actual thing we're going to be doing. That
Right.
you're absolutely, there would be some weird jagged quantized of edge effects that we need to worry about for small numbers, but we won't have to worry.
And we're of course we're quantizing it on on n without the string because that's
Right.
the energy. It's not
Exactly. Exactly. That's what's going to set the energy in. That's right. That's right. We don't care about the individual components. We only care about the total energy, and that's set by n and not any of the numbers. That's right. Yep. We good with this? Cool. So let's solve this for n in terms of the total number of electrons. N is, just solving this for n and combining terms, we get 3ne over pi to 1/3, which is kind of a nice, simple result. So we can plug this in for n, because this is the total number of electrons in your soup now. This is a measurable quantity. This gets us to a Fermi energy of h squared over 8ml squared times 3ne over pi, all to the 2/3 power. Just plugging this in for that. Okay, what's next? This isn't really what we want either. We don't want the total number of particles in our soup. We want the number density of particles in our soup. That's a measurable and physical quantity. We don't actually have a box. We want to now break out of the box and think about this in terms of densities and not total number of particles. So let's set the number density of electrons to be the total number of electrons divided by L cubed. And H bar, people like H bar, so let's do the H bar conversion. H bar squared, of course, is H squared over 4 pi squared, and plug this in for NE and this in for H, and you get epsilon Fermi energy is 4 pi h squared over em times 3 and e over pi L cubed, all to the 2/3 power. And, oh, I guess I didn't do this one, but I will. This is pi h bar squared. This is an h bar. Although my eyesight's getting bad enough, it's hard for me to differentiate between h bar and h. Sorry, let me write this down. We've got pi cubes and pi's, we've got n's, so 2/3. Anyway, I should just written down the last one and let me do it. Fermi energy is equal to h bar squared over 2m times 3 pi squared little n, number density, to 2/3 power. And this is a general result. This is the Fermi energy of any fermion with mass m and number density n, irregardless of whether it's in a box or not. Again, this doesn't tell you the energy of a particular fermion or even the energy of the fermion gas itself. But this tells you the minimum energy, or it tells you if you have it completely degenerate and you set it to t equals 0, what the maximum energy of the particle in that sequence is. If you have a completely degenerate gas, it tells you where this step function will happen for a particular particle. And it's dependent on the mass of that particle inversely, and on the number density of those particles in that area, to the 2/3 power. We're going to do one more astrophysical substitution, which is that we are much more usually interested in mass densities rather than number densities. Let's just make this a mass density instead of a number density. We know that Ne is the number of electrons per nucleon times the number of nucleons per volume. And this is I'm not sure this follows directly from this, but let's see if we can unpack this. Z over A times rho over MH. Z being the total number of protons. A being the atomic number, oh, wait, no. A is atomic mass. How do you
For
define
nucleon, not nucleus. So we would, A would be atomic, like,
Yeah, so Z is the total number of protons in the nucleus, and A is the atomic mass of the nucleus. Right. So if we assume that for every proton there's an electron, then the number of protons, this is counting the number of protons should be the same as counting the number of electrons. And this should be counting the number of protons, number density of protons. So this is the total mass density divided by some scale factor. this is the mass per nucleon of the proton, no, the number of protons per, this is the fraction of nucleons that are protons. And this is the total net density divided by the mass of hydrogen is one of those protons. This gives you the number density of proton, which is the same as the number density of. I think that's reasoned out and appropriate. So this gives an astronomer's version of this, which is h bar squared over 2me 3 pi squared times z over a times rho over mh. The 2/3, now I've got a mass density in there and z's and a's, which is what we're used to thinking about in terms of absolute. And these are all constants, except for z and a and the mass. So at t equals 0, all electrons have energy less than the Fermi energy. But t is not equal to 0, right? Obviously, these are some very, very hot astronomical contexts that we're talking about. So when do we need to worry about this effect? When do we need to worry about degeneracy? And when can we ignore it? We need to know at what temperature this effect starts to become important. How do we know what T not equal to 0? It's emphatically not equal to 0. When do we need to worry about it? Okay, now we need to bring in some thermal physics. Energy of a typical electron in a thermalized gas is 3/2 kT. We've derived that numerous times. I hope I've derived it numerous times for you in your college career. So if 3/2 kT is less than the Fermi energy, then we need to start taking this seriously. That means that you would be building up a Maxwell-Boltzmann distribution whose peak was about the Fermi energy, and now you have to worry about this stuff. So this is not a bad, certainly if this is the case, then you need to worry about degenerate physics. So let's see if we can come up with a temperature gauge for this. So we need 3/2 kT to be less than that thing over there. H bar squared over 2me 3 pi squared times z over a rho over mh, all to the 2/3 power. So let's pull out Z and A will change, but not by a lot. It's really the temperature and the density that are going to matter. Let's pull all the things that are kind of constants over to the right and pull all the things that are not constants over to the left. So that's really just the T and the rho. T over rho to the 2/3 must be less than H bar squared. And let's combine all the constants over here. We've got 3 MEK, and I've got 3 pi squared over MH, Z over A. all to the 2/3 power. Let's think about what this Z over A is, though. Maybe we can even make some more assumptions. What's Z over A for helium-4? 1/2. 1/2. What's Z over A for carbon-12?
1/2.
1/2. What's Z over A for oxygen-16?
1/2.
Yeah, you get the idea. Most of the things that we're going to be making these white dwarfs out of have Z over A of 1/2. We can plug 1/2 in for Z over A and probably get a pretty good handle on what this number is going to be. And then everything on the right-hand side is a constant. So for Z over A of 1/2, we can write down T over rho to the 2/3 power is less than, plug in 1/2 for this, plug in numbers for all of these things with units. What do we get? We get 1261 kelvins meters squared per kilogram to the 2/3 power, which is a weird unit and not at all intuitive what this means, but it's a number. It's a number. If you know your density, your mass density of this thing, and we do for a white dwarf, for a typical white dwarf, we can figure out at what temperature things degeneracy is unimportant. It's just a number. And the smaller the value of T over rho to the 2/3, the more degenerate the gas is. And by more degenerate, I mean closer to having this step function of energies and less like a Maxwell distribution of energy.
Could you say what this expression was again? To me, this was like 26 km squared,
1261.
1261. Okay, so
This is just a number.
Okay.
I've just combined all of these constants together in SI units and added 1/2 for Z over A.
Okay.
That's really all I did. It's just a number. Okay, so for the last thing today, let's look at, this is a fun diagram, and we can sort of start to begin to understand it now. Thanks for that. Okay, so so we've seen how the sun evolves from pre-main sequence to death on the HR diagram, but the HR diagram is a surface property diagram. What is the temperature at the surface? What is the luminosity, right? This is what we think happens at the core of the sun as it ages. This is probably a much more important and useful diagram for calculating, for understanding how stars work, right? We've got the central temperature in Kelvin on the y-axis, and we've got the density on the x-axis. And not surprisingly, there's a regime here that's degenerate, and there's a regime here that's not degenerate, right? And we expect, because it's temperature versus density, this is a power of 2/3, there should be some slope that separates those two regions. And indeed there is, that's that dotted line. If you work this out, a low value of T over rho to the T over rho is going to be the right-hand side of this dot. This is the Fermi, this is that greater than or less than boundary. Over here, it's less than, over here it's greater. So here's the sun right now as a main sequence star. Non-degenerate, not highly degenerate at all. You can do it fairly good without it. But fairly quickly, once you reach the subgiant range and you stop generating energy, you contract, the temperature doesn't go up much, and the density goes way up. And that gets you firmly into this degenerate regime until you really can't squeeze it together anymore. Temperature goes up. Core flash happens way over here, way in the degenerate part of the spectrum. It moves quickly back over here. Non-degenerate. This is the horizontal branch. You're burning helium in your core. You go through some helium core burning stuff. Who knows what this is? The asymptotic giant branch. You move back toward the degenerate planetary nebula. And the physics here is dominated by degeneracy on this side and non-degeneracy on this side. So I'll stop there because I'm already over. We'll talk next time about how we can apply this to white dwarfs and the context of white dwarfs and figuring out how massive they can be. Cool. See you Wednesday.